Now let us do an example that is slightly more involved. Let's take a look at the splitting field of the polynomial x to the power 4 minus 3 over the rationals. So how can we draw a picture of the splitting field over Q? So obviously we can adjoin one element, which is the fourth root of 3, and this will be a degree 4 extension over Q. But unfortunately, this extension is not Galois. So what are the other roots of this polynomial? Well, x to the 4 minus 1 factorizes as x minus 1. Well, let's factorize it as the difference between two squares first. X squared minus 1, x squared plus 1. X minus 1 factorizes as x plus 1, x minus 1. And x squared plus 1 factorizes as x plus I, x minus I. So if we wanted to factorize x to the 4 minus 3, we could factorize it as the fourth root of 3, x plus the fourth root of 3, x plus I times the fourth root of 3 minus I times the fourth root of 3. So the conjugates of fourth root of 3 are minus the fourth root of 3, I times fourth root of 3, and minus I times fourth root of 3. So if we wanted all of these roots in one field extension, we would also have to adjoin I to this field. And once we've done that, we've got all four roots. In other words, this is a Galois extension over Q. So adjoining this element I is a minimal polynomial x squared plus 1, so degree 2. And the degree of this intermediate field over Q is 4. Can you see any intermediate fields between Q and Q adjoined fourth root of 3? That's right. If you square the fourth root of 3, you get the square root of 3. And now we've broken up this degree 4 extension into two degree 2 extensions. Okay, can you see any other quadratic fields over Q? Well, I is in the ultimate extension, so we will have to adjoin I to Q. So that is another degree 2 extension. And as we've seen in the previous example, if we've got one extension with I, one extension with Q square root 3, then we can put them together in one degree 4 extension that has both of them, and there's another intermediate field which is attained by adjoining their product to Q. So we've got a bunch of degree 2 extensions in this picture. What does the Galois group on the other side look like? Oh, we've got identity. This extension is Galois of degree 8, so we expect a group with 8 elements. So let's write down, see if we can write down a few of them. So clearly one of them is complex conjugation. We can map I to minus I, and then keep the fourth root of 3, which is a real number fixed. And if we apply sigma twice, we get back to the identity automorphism. What else can we do? What other type of automorphism do we have? Well, there should also be an automorphism that maps the fourth root of 3 to one of its conjugates. So let's say it maps it to I times the fourth root of 3, and let's say that this one keeps I fixed for now. What is the order of this automorphism tau? Order of sigma is 2. What's the order of tau? Well, to establish this, let us work out what tau squared would be. The tau squared takes I, maps it to I, and then maps it to I again after that. it takes fourth root of 3, maps it to I times fourth root of 3, and then if tau is applied again, it maps I to I and fourth root of 3 to I times fourth root of 3. So actually tau squared maps it to minus the 3. As an exercise, you can show that tau cubed then maps it to minus I times the fourth root of 3, and tau to the 4 is the same as the identity. Okay, but this is only 4 automorphisms, and we claim that the automorphism group has order 8. Well, actually, we've forgotten the identity so far. The identity acts trivially. So now we've got 5. Can you identify the other 3 elements in the automorphism group? One possible way to write them down is to say tau sigma, tau squared sigma, and tau cubed sigma. One alternative way would be to reverse the order of tau and sigma, but I'll address that in a minute. So what does tau sigma do to I? Well, tau after sigma, and sigma maps I to minus I, and tau maps I to I, tau sigma maps I to minus I. What does it do to the fourth root of 3? Well, sigma maps fourth root of 3 to 12, and tau maps fourth root of 3 to I times. And as an exercise, you can show that tau squared sigma acts by sending I to minus I, and fourth root of 3 to minus fourth root of 3. Tau cubed acts by sending fourth root of 3 to minus I times fourth root of 3. What would happen if we reverse the order of sigma and tau? Let's see what happens if we were to work out sigma tau instead of tau sigma. Well, if it acts on I, tau acts trivially, so this is the same as sigma pi, so we end up with I. If we act on 3 instead, tau maps that to I times 3, because sigma is a homomorphism, same as sigma applied to I times sigma applied to fourth root of 3. Sigma maps I to minus I and keeps fixed. So it maps I to minus I and fourth root of 3 to minus I. This shows that sigma tau acts in the same way as tau cube sigma, and not the same as tau sigma. This illustrates that the Galois group is non-abelian. Okay, so let us work out all the subgroups of this group. So clearly the full group is generated by sigma and tau. So we've got that at the bottom. What field is the fixed field under all of the automorphisms sigma and tau? Well, only the rational numbers. What are the other subgroups? Well, let us list a few of them over there. So we've got the group generated by sigma. We've got the group generated by tau. So this has order 2, order 4. We've got the group generated by tau squared. That has order 2. See if you can fill in the rest of them. So let's see if we can fill in these subgroups on the other side of this diagram. So what field is the fixed field under sigma? Well, again, the most systematic way to go about it is to show how sigma acts on a basis. So what is a basis for this big field over Q? Well, we can write, well, 1 is an obvious choice, I, 4th root of 3, perhaps the square of the 4th root of 3, which is the same as square root of 3, perhaps the cube of this, and then I times all of them. Actually, let's move the I to the right-hand side. I times, sorry, just I times 3 times I 4 root 7. So how does sigma act on each of them? Well, it keeps this first 4 constant because they are all real. It maps I to minus I. That means it mutes line of each of the last 4. In other words, if we wanted the fixed field, it would be the field generated as a vector space by these first 4 elements. And that is Q adjoin the 4th root of 3. So in our picture, the group corresponding to the 4th root of 3 is the group generated by. So that's in our picture there somewhere. This is a group of order 2 that corresponds to the fact that the index of the field Q 4th root of 3 is inside Q adjoin I 4th root of 3 with index 2. Let's see if we can go further. There was one other group of order 2, that's the one generated by tau squared. Let's see if that corresponds to Q adjoin I and square root 3. So let us fill in this table. What will tau of x be? Of tau maps 4th root of I times 4th root of 3. So if we square that, it becomes minus 4th root of 9, and if we multiply that by I times the 4th root of 3 again, we get minus I. I is actually mapped to back to itself. I times the 4th root of 3. Well, I is mapped to I. The 4th root of 3 is mapped to I times the 4th root of 3. So multiplying them together means that this is mapped to minus 4th root of 3. I times 4th root of 9 will be mapped to I times minus the 4th root of 9. So that will be minus I times the 4th root of 9. And in the last column, I is mapped to I, and the 4th root of 27 is mapped to minus I times the 4th root of 27. If we multiply I with minus I, we get 1. So in order to get something fixed under tau, we would have to generate some linear combination of 1 and I. Everything else is mapped to something different. In other words, the group tau corresponds to this field Q adjoin I, so that is the second part of our diagram. Right, let's do the tau squared after this. So 1 is mapped to 1, I is mapped to I, fourth root of 3 is first mapped to I times the 4th root of 3, and after that it is mapped to, well, I is mapped to I, and the fourth root of 3 is mapped to I times the fourth root of 3. In other words, the composite tau squared maps fourth root of 3 to minus fourth root of 3. Right now, fourth root of 9 is just that one squared, so it maps fourth root of 9 back to itself. It maps the fourth root of 27 to the product of these previous two columns, in other words, minus the fourth root of 7. And now we can put them together with I in these minus I times the fourth root of 3, I times the 9 minus 27. In other words, if something is fixed under tau squared, it must be generated by 1, the square root of 3, I, and I times the square root. In other words, fixed field under tau squared is Q adjoint square root of 3. Right, so we've got that next part of our picture. So one can continue this, and I'll leave it as an exercise to fill in the rest of this diagram. There are two more subgroups to determine. One of them will be this subgroup generated by sigma tau. So it will be sigma tau, sigma tau, which is, but it will be more convenient to use tau sigma. So the identity tau sigma squared, which is tau sigma, which is tau sigma. And we saw earlier that let's group them in this way, the sigma tau in the middle. We saw earlier that sigma tau is the same as tau cubed sigma. So this is the same as tau times tau cubed sigma, which is 4 sigma, which is, so sigma will be a next element in this group. And then clearly if we multiply sigma on the right with tau sigma, we get tau sigma squared, which is equal to tau. And the other subgroup will be the one generated by tau cubed. Its square will also be sigma, and its cube will be tau cubed. Just check that the orders of the groups and the indices of the fields correspond in the correct way. Orders of the groups are 4. Is it in the correct side? Is it the index with the top or the index with the bottom that matters?